The last idea we're going to look at with integration is the idea of symmetry. We talked a bit about this already with odd and even functions and what have you. So if it's an even function, formally the definition, function minus x is equal to function x. So that means you've got symmetry in the y-axis. So if you want to integrate from minus a to a, you could just do twice from 0 to a. Now, of course, if you have a horizontal shift, the symmetry still exists. So if you had this sort of situation, if you've shifted everything across C units and you'll notice that you're integrating an even amount on either side of C, so C minus a to C plus a, you could still use the idea 2 times the integral from C to C plus a. Is that going to be useful? I guess it depends what the numbers are, how easy C and C plus a and things like that are to substitute in. Could be useful for trig functions, I suppose, because if you shifted it across, you might still have that, oh, well now I can substitute in a pi on 2, which gives me 0 or something like that. But anyway, will you use it? Who knows? But it's there. That idea is there. Obviously the even part, that's important. So the odd part also has symmetry. Remember, it has rotational symmetry, so function negative x is equal to negative function x. So that means that integral will always equal 0. Right? If it's area we're talking about rather than integral, then it's like the even function, you can go twice 0 to a. But if it's straight integral, you can save yourself a lot of time and go, oh, hang on, I recognise I've got the rotational symmetry there, I don't need to work out this integral, I know the answer is going to be 0. And again, if you notice a horizontal shift happening, that one probably would be more useful, I guess, than the even one, because if you do notice that, again, you could look at it and say, oh, well, that's going to be 0. Saves me integrating the whole thing. A rare occasion, but who knows? You never know what's going to happen. The third one, which we haven't really talked about, is this. Let's prove it formally. I'll just do it by substitution. If I let u equal a minus x, du is minus dx. The limits, when x equals 0, u would equal a, x is a, u is equal to 0. So we end up with minus the integral from a to 0 of function u to u. I can get rid of the negative by swapping the limits around. And because it's a definite integral, it doesn't matter what the variable is, because we're going to substitute into it anyway. So function u to u is the same as function x dx, thus proving those two integrals will give you the same amount. So there's a formal proof of the idea. Now, keep in mind this when we're dealing with symmetry. Remember, if it's the same type of function, so both odd or both even, when you multiply them together, you get an even function. If they're different types of functions, one's odd, one's even, you'll get an odd function. So we get a question like this. Now, prior to a few days ago, we would have just looked at that and went, how the heck am I going to do that? Problem is now that we have all our techniques, the temptation is to go, sine cubed, all right, to work out sine cubed, I'll go and withdraw the signs and do all that. But if you recognise it as an odd function, because it's sine cubed, well, sine is an odd function. And we just said odd times odd gives me an even, but then this is times another odd one, so even times odd, it is an odd function. So I don't need to do anything, that's just 0 straight away. Don't need to do any integrating. Okay, integral from 0 to 1 of x squared 1 minus x. This is where I'm going to use that last idea. Because, you see, you've got the square root of 1 minus x. But I notice, look, it's going from 0 to 1. So everywhere I see an x, I can replace it with 1 minus x, which means I'll get the square root of a single term underneath. It'll become 1 minus x squared root x. And that's easier to integrate because I can just expand that out and it ends up being a simple add 1 to the power over the power. Substitute in the 1, substitute in the 0, and we get our answer. So a lot quicker than trying to integrate x squared times the square root of 1 minus x. Well, a lot might be an exaggeration, but it is quicker. Improper integrals. Okay. So if the function, the integrand that you're integrating is undefined at some point, or unbounded, we mainly deal with infinity, I suppose, because technically you can't substitute infinity into a function. So we'll use limits if a solution exists. A solution might not exist. That is, of course, a possibility when you're integrating to infinity. It might have an infinite area. So something like that, the integral of dx on x, so our hyperbola over there, we're going from 0 to 1. But of course, we can't find the log of 0. And we know that when we integrate this, we'll get a log function. So what we're really saying is the limit as n approaches 0 from n to 1 of dx on x. So we'll get our log function. We'll get minus log n when I substitute in, because it'll be the log of 1, which is 0, minus the log of n as n approaches 0. Well, and this is a case of where, no, it's still not going to come up with an answer here. It's not going to give us an answer because the log of 0 is also undefined. So this integral, no, we can't work that one out. That's undefined. But this one, I could. So integral of x e to the minus x squared, if I was going from 1 to infinity. So really, I guess the way I think about it is, it's the limit as n approaches infinity of the integral of 1 to n, and I'll just integrate that one. And of course we have derivative times function there, so minus half e to the minus x squared. Substitute in the n, substitute in the 1. Now if you think of your curve e to the minus n squared, so e to the minus positive constant, well, it's just going to be our exponential curve, which is backwards, reflected in the y-axis. So as we're approaching infinity, that curve is approaching 0. So that would just then be 1 on 2e, because the e to the minus n squared would approach 0. Another idea that we use, and we have seen a little bit of, is this idea of playing with inequalities in area. So I want to find an inequality, and we said, the outer rectangles, inner rectangles idea, we could trap it in between the two. And that's what this is basically saying. If I know a particular function is in between two other functions, between a and b, then the value of the integral between the two must also be in between the two. 2009 paper, 8b, which of course back in 2009 that was the last question on the paper. So there's our graph, y equals 1 on x, and they've taken one particular rectangle there, going from n minus 1 to n, and they've dotted in the outer rectangle and the inner rectangle as well. We want to show this wonderful inequality here, that e to the minus n on n minus 1 is less than 1 minus 1 on n to the power of n, which is less than e to the minus 1 itself. All right. So I'm going to use that idea. I mean, they've drawn a lovely picture for me. Seems to be the obvious thing to do, but I'll say, well, the area under the curve will be in between the inner rectangle and the outer rectangle. So the area of the inner rectangle will be 1 times 1 on it. Its width was 1, and height would be whatever the function value is at n. On the right-hand side, the outer rectangle, its width is also 1, but its height would be the function when we substitute in n minus 1. So we know that integral is in between those two things. Well, let's work that out. The multiplying by 1 is easy. Then the integral in the middle, once again, dx on x, turns out to be log x. If I substitute in the n and n minus 1, I've done it all in one hit. I mean, I get log n minus log n minus 1, but then I've combined it into one log function. So 1 on n is less than the log of n on n minus 1 is less than 1 on n minus 1. I've multiplied everything by n. So the left-hand side becomes 1, the right-hand side becomes n on n minus 1, and we get n log n on n minus 1, because actually that n I'm going to put back into the log, and I get n on n minus 1 to the power of n. Now, I know y equals e to the x is a continually increasing curve. So if the numbers that I substitute in are in this order, then their answer should also be in that order as well. So I exponentialize, if that is such a word, everything. So e to the power of 1, e to the power of log, well, e to the power of log cancels, and I just get n on n minus 1 to the power of n, is less than e to the power of n on n minus 1. We're getting close to what they wanted, still not quite there. Going to turn everything upside down. But when you take the reciprocal, you've got to change the inequality sign, remember. So now you'll notice we have greater than signs, which looks a bit funny. So let's put it back the way it should look. But also I've made use of negative indices as well. So the 1 on e became e to the minus 1, and the e to the power of n on n minus 1 became e to the negative n on n minus 1. And that is what they asked us to prove. So there we go, the last of the exercises. Now, you'll notice here, I did the formula a minus x, with that function a minus x. The text, well, I should say the text, has 2a minus x. Again, that's all to do with that symmetry. Because when you, and we'll see this when we look at drawing graphs, the function 2a minus x represents a reflection in a, which is easier to say than a minus x is a reflection in a divided by 2. I mean, it's the same thing, but it just hasn't got fractions in it.